Greetings everybody. I believe this is video 5 for Exam 2 Practice 1. And now it's problem 4 because it's another UCM problem. And it's a classic UCM problem called the dryer problem. Where here you have a clothes dryer, okay? And the rate it rotates, and the rate of rotation is chosen so that a small piece of clothing will lose contact with the tub. It will no longer be in contact with the wall of the tub when it reaches an angle of 67 degrees, an angle of theta equals 67 degrees above the horizontal as shown. So it's happening, this is the wall of a dryer. So what happens is as it's rotating, every time the clothes hit that angle there, they fall to the bottom of the dryer. When they get to that angle, they fall to the bottom of the dryer. They lose contact with the tub. Okay, so if the radius r of this tub is 0.335 meters, what rate of revolution is needed? How fast is the dryer tub rotating in terms, and I want it in revolutions per minute. Well, what's going on is the piece of clothing is undergoing UCM. It's spinning in this dryer tub. It's undergoing UCM. But every time it gets to this location at an angle theta above the horizontal, every time it gets there, it falls to the bottom of the tub, but then it undergoes UCM again. So we need to, let's go ahead and let's draw all the forces acting on the piece of clothing and then apply Newton's second law for UCM. Okay, well here's the piece of clothing. Okay, well what two forces are acting on it? Well, there's the weight of the clothing, mg, in the blue here, acting again straight down in the negative y. And the only other force acting on the piece of clothing is the normal force. It's the force of the dryer pushing on the piece of clothing. So you have mg and Fn. Now remember, the piece of clothing is undergoing UCM. So notice Fn is already directed towards the center of the tub, of the circle. Now what about mg? Well, we need to take mg and we need to resolve it into its components. One component is going to be in the radial direction, which is the red. The other component of mg is going to be perpendicular to the radial direction in the purple. So you have to take mg and resolve it into its radial component, which is the red, and then perpendicular to that, which is the purple. Now I'm calling this angle in here, I'm calling it alpha. Okay, well notice clearly the angle alpha is 90 minus theta. Because you can look at this, with the dotted line and then the blue and the red. That right triangle, clearly alpha is 90 minus theta. And because theta is 67 degrees, alpha is going to be 23 degrees. You don't have to do that, but I'll use the angle alpha. So now notice, with mg, I'm resolving mg into its component in the radial direction, which is the red vector, and the component perpendicular to the radial direction, which is the purple. That's why I want to use the angle alpha. It makes it a little bit easier. Well, notice the purple component, the component that's perpendicular to the radial direction, that's opposite alpha. So that's mg sine alpha. The adjacent component, the component of mg that's along the radial direction, is this red vector. That's mg cosine alpha. So purple is mg sine alpha, red is mg cosine alpha. Well, remember, what is alpha? Alpha is 90 minus theta. So there's just a basic trig identity so we have the radial component is mg cosine alpha, or mg cosine 90 minus theta. Well, the identity is the cosine of 90 minus theta is the sine of theta. And likewise, the purple component is mg sine alpha. Well, what is alpha? Alpha is 90 minus theta, so it's mg sine 90 minus theta. Well, the sine of 90 minus theta is cosine theta. just basic trig, but it's just easier to use the angle alpha because clearly the purple is mg sine alpha and the red, the one we need, is mg cosine alpha. And because alpha is 90 minus theta, you just have this trig identity for each of them. Now let's look at Newton's second law for UCM to the piece of clothing. The sum of the forces in the radial direction must equal mv squared over r. Well, right now, let's look at our diagram. There are two forces in the radial direction. There's mg sine theta, which is pointing towards the center, and there's Fn. Clearly, there's two forces, the red vector and the green vector. And they're both positive because they're both directed towards the center. So I have mg sine theta plus Fn equals mv squared over r. Now remember, they tell you that when theta is 67 degrees, the piece of clothing will lose contact. That means that at that angle theta, Fn will become 0. Because if it loses, remember, Fn is the contact force. The object has to be in contact with the surface. So if a piece of clothing loses contact, Fn goes to 0. So you get mg sine theta equals mv squared over r. Let's solve for v and then convert it to revs per minute. Well, the m's cancel, and you get, m's cancel, multiply both sides by r, take the square root. You get v equals root gr sine theta. R was given as the 0.335 meters. G is 9.8 meters per second squared. Theta is 67 degrees. And you get V is 1.74 meters per second. Then you just want to convert that to revolutions per minute. Well, 1.74 meters per second. And we know the dryer, it's one revolution. For every one revolution represents a complete circle of length 2 pi r, which is going to be in meters, because it's one rev for every, one revolution means one circle, so it makes one rev for a distance of 2 pi r. That's what that means here. And in the numerator, in the denominator, the units of the 2 pi r are in meters. So again, it makes one rev for every 2 pi r, and then there's 60 seconds in 1 minute. So meters cancel with meters, seconds cancel with seconds. So 1.74 times 1 times 60 divided by 2 pi r, and you get, it makes 49.6 revs per minute, or it's rotating about 50 times every minute. And don't let this trig confuse you. We're just using the angle alpha to component mg because I've got this right triangle, and if that angle in there, if that's the angle alpha, the opposite is mg sine alpha, and the adjacent, the one we need, the one that's in the radial direction, that's mg cosine alpha. And you can keep it like that. You can use mg cosine alpha instead of mg sine theta because they're exactly the same. Remember, alpha is 23 degrees, theta is 67. But basically you have to resolve mg into, if one component is going to be in the radial direction, that's the red vector. The other component of mg is going to be perpendicular to the radial direction, that's the purple. You don't need the purple, you just need the red. And then you have Fn, but when the piece of clothing loses contact, Fn goes to 0. So let me go ahead and save this video and get it posted.